Hi, it's Kemgal. In this video, we're going to talk about naming, aka nomenclature. When we name organic structures, we use something called the IUPAC system. Each compound has its own identity and unique behavior, so we name these structures based on their unique characteristics. In order to name, I use something called the FUPSS method. FUPSS. FUPS stands for Functional Group, Unsaturation, Parent Chain, Substitution, and Stereoisomerism. So we're going to talk a little bit about each of these before we get started. These are most of the functional groups you want to be aware of. First off, we have carboxylic acid, and this group consists of a COOH group. And I want to take a moment to look at the C double bond O group here. This specific group is called a carbonyl group. So now we can say that a carboxylic acid consists of a carbonyl group with the carbonyl carbon bonded to OH. And whenever you have a structure that contains a carboxylic acid, you're going to find that its name has the suffix oic acid. Next off, we have aldehydes. And so aldehydes have a carbonyl group with a hydrogen attached to the carbonyl carbon. And whenever a structure has an aldehyde in it, it has the suffix al. Now we have a ketone, and a ketone consists of a carbonyl group, but this time it's bonded to two R groups. And what is an R group anyway? An R group is an arbitrary term that represents any alkyl group that the structure could be attached to. So for instance here, we could have long carbon chains. And whenever a structure has a ketone, we say that its suffix is going to be ONE, one. Next, we have alcohol. So an alcohol is really easy to spot because it's just an OH group. And whenever a structure has an alcohol, it's going to have the suffix ol. Next, we have amines. And so an amine is just an NH2 group. An amine is really easy to memorize because its suffix is just going to be amine, just like its name. And finally, amides. And so the difference between an amine and an amide is that an amide has a carbonyl group in it. And so its suffix is also going to be the same as its name. It's going to be amide. So that's it for your functional groups. Now I can walk you through each and every one of these, but you must sit yourself down and memorize what each functional group looks like and its respective suffix. I know it might seem overwhelming memorizing these functional groups, but with practice, you will have this down in no time. Now it's time for unsaturation. And unsaturation is just a fancy way of saying double or triple bonds. So if your compound has unsaturation, it likely has one or more double bonds or triple bonds. So an alkane has all single bonds, and so it's going to have the suffix -an. An alkene has one or more double bonds, and it's going to have the suffix -ene. An alkyne has one or more triple bonds, and it's going to have the suffix -ine. Now, parent chain is a little bit easier to memorize. So if your parent chain consists of one carbon, it's going to have a prefix of meth. If it has two carbons, it's going to have a prefix of eth. 3 carbons, prop, 4 carbons, bute, 5 carbons, pent, 6 carbons, hex, 7 carbons, hept, 8 carbons, oct, 9 carbons, non, 10 carbons, dec. And you could just sit and memorize these rather easily. Let's take a look at an example. Here we have pentane, and we're going to dissect its name. So for the first part of this word, we have pent. And now you can recognize that pent stands for its 5 carbons. It has a 5-carbon parent chain. What about an? What does an stand for? So an actually stands for the fact that it's an alkane, meaning it's all single bonds. So you can recognize that here. Another way of saying this is that it has 0 units of unsaturation. Now what about E? What does the E stand for? So the E stands for the fact that it has no functional group. So we didn't mention this before, but when a structure has no functional group, it actually has a suffix of E. So now you can see that every fragment of the name tells us something important about the structure. Now we're going to show you how to determine a structure's name, but before we do that, we have to go over one last thing. That is stereoisomerism. And so that's just a fancy way of saying whether something is cis or trans. So this right over here is cis and this right over here is trans. And I'm going to show you how to tell the difference. So what I like to do when I like to determine whether something is cis or trans, I like to cut the double bond in half like a sandwich. So I cut my sandwich in half and I then like to draw in my hydrogens. So I know that I have a hydrogen here and I have a hydrogen here. And then I look to the left of my sandwich and I ask myself, who is the heavier group? Is it going to be the CH3 group or is it going to be this hydrogen? And it's actually going to be the CH3 group. We know that a CH3 group here is way heavier than a hydrogen by itself. Now I look to the right of my sandwich and I ask myself, who's the heavier group? Is it this hydrogen or is it the CH3 group? And again, we know that CH3 is definitely heavier than the hydrogen. So therefore, I see that my two heaviest groups are on the same side. So when the two heaviest groups are on the same side, we say that this is cis. And an easy way to remember that is the alliteration. Same side, cis. Now what about the other example for trans? Well, let's go ahead and cut it in half like a sandwich again. So we cut our sandwich in half and we draw in our hydrogens. So I know this carbon has one hydrogen here and this one has one here. And now I ask myself, who's the heavier group on the left? Is it hydrogen or is it this methyl? And we can all agree that the methyl is the heavier group. And now I ask myself, who's the heavier group? Is it this CH3 group or is it this hydrogen? And we can all agree that the CH3 group is the heavier group. Therefore, we see that these two groups are on the opposite side. And so we say that when they're on the opposite side, they are trans. Fun fact, some chemists like to call cis Z and trans E. So if you ever see Z in a name, you know that it's cis. If you ever see E in a name, you know that it's trans. And a funny mnemonic that you might hear is "Zis is cis," and that's something that helps people remember that Z is cis. So now let's look at some examples and see whether or not these guys are cis or trans. So to start us off, I like to cut the double bond in half. So first I cut the double bond in half, and then I draw any hydrogens that are on that double bond. And so I see that I have one here. So now I ask myself, who's the bigger group? Is it this hydrogen here, or is it this carbon attached to two other carbons? And clearly we can see that this guy is going to be a way heavier group. So we can go ahead and circle that. And now I look to the right of my structure, and I ask myself, who's the heavier group? The CH3 or this guy? And we can totally see that the ethyl is the heavier group. So what do you think? Is this cis or is this trans? Well, we see that both the heaviest groups are occurring on the same side. Therefore, we can say that this guy is cis. Or we can say he's Z. What about example number 2? So in example number 2, we can cut the double bond in half, right? And we ask ourselves, who's the heavier group on the left? Is it the CH3 group or is it this guy? And clearly we can see that this guy on the bottom is way heavier. So we can go ahead and circle that group. And what about on the right? We have this guy attached to an alcohol group in a CH3, and on the bottom we have this CH3 group. So clearly we see that the top guy is heavier. So now we can see that these groups are occurring on opposite sides. And so we say that this guy is going to be trans, or E. Now, time for example number 3. So sometimes people get confused, and a common mistake that they'll do is they'll cut their double bond in half like this, and they'll ask themselves, oh, what's my heavier group? Is it this guy or this guy, right? But remember, this is the wrong way to cut your double bond. You want to cut it in half like a sandwich, right? Like this guy is a sandwich, and you're cutting it in half. As if you have a grilled cheese here, and you're cutting it in half. So now you can ask yourselves on both sides, who's heavier? So we look to the left of our sandwich and we see we have this carboxylic acid and this hydrogen. And clearly you can say that the carboxylic acid is way heavier than the hydrogen. Therefore, this guy is going to be the heavier group. And if we look to the right of our double bond, we have a hydrogen and a CH3 group. And so who's going to be heavier? It's going to be the CH3 group. So now we can say that this guy right over here is trans. Let's go to example number 4. So remember, we cut it in half like a sandwich, and we can draw in our hydrogens, and then we'll ask ourselves, we look to the left and we say, who's going to be the heavier group? Is it this ethyl group, or is it this ketone group? And so clearly the ketone group is a lot heavier. Oxygen actually has a greater atomic mass than carbons and hydrogens, so this guy's going to be a lot heavier. And if we look to the right of the structure, we see that we have hydrogen and a CH3 group. And when we ask ourselves who's going to be heavier, we know that the carbon is going to be way heavier. So now we see that these are occurring on opposite sides. Therefore, these are trans. Now on to the next example. When we split this double bond in half, we see that it has a few hydrogens in here. And so what's happening here, when we look to the left, we ask ourselves, who's the heavier group? Is it hydrogen or this guy? And we clearly see that the bottom group is way heavier. So we can go ahead and circle that. This group is heavier. And what about to the right? What's going on here? Well, we have a hydrogen competing against another hydrogen. So who's heavier? Trick question, they're actually both the same mass. So technically, we cannot assign stereoisomerism here because this group is equally heavy as this group. So what do we say in this case? It's actually a long word. We say that this double bond is non-stereoisometric. That means that it wouldn't be cis or trans. Now on to our last example. Would we be cutting this structure like this, vertically, or would we be cutting it like this, horizontally? The answer is we would be cutting it horizontally because you want to cut it as if it's a sandwich. So if you need to turn your head a little bit to see it, that's fine. So now we fill in our hydrogens, and we gotta look to the left of the sandwich. So we ask ourselves, who's going to be heavier, this hydrogen or this guy? And we can clearly see that this guy is going to be the heavier group. So we can go ahead and circle it. And onto the right of our sandwich, supposing your head is turned, we can ask ourselves who's going to be heavier, this guy or this guy? And this guy is just a CH3 group, but this guy has a lot more business going on, right? So we can clearly see that this group is going to be way heavier. So we can go ahead and circle it. And now we see that the two heavy groups are occurring on the same side. And so we call this cis, aka Z. So now you have successfully assigned cis and trans to all of these. Now here I have the first example that we just assigned cis and trans to. And I want to show you how we use the FUPSS method, FUPSS, to go ahead and name this structure. So let's go ahead and name this structure. We always start by numbering our parent chain. And we want this to be the longest possible chain that we can make. So if we go ahead and number this guy 1, 2, 3, 4, 5, 6, we see that it's made of 6 carbons. But we can actually make it longer. We can say we got 1, 2, 3, 4, 5, 6, 7. And that way we have a parent chain of 7 carbons. But now should we number it going to the left or going to the right? So I'm going to go ahead and copy this guy to see which direction is better in this specific situation. So if we go ahead and number it from the left, and here we can number it from the right, what do we see? So when comparing which situation is better, we want to look at the double bond and the substituent. And you're probably like, hold up, what's a substituent? So let's back up for a minute. Anything coming off of the parent chain, such as this guy who doesn't have a number, is considered a substituent. when we want to look at which direction is better, we have to look at our double bond and our substituent. Our double bond and our substituent. And we ask ourselves, well, which location has the lowest numbers? And so here we see that this double bond is occurring at 4 and 5, whereas this double bond is occurring at 3 and 4. So who's going to have the lower number? And so 4 and 3 is actually the lower number because 3 is less than 5. And so if we're looking at our substituent, we see that this substituent is coming off of carbon number 5, and this substituent is coming off of carbon number 3. So who's better? This substituent, right? Because it has the lower number. So the lower the numbers are, the better. So we're going to go ahead and say that this guy is the way to go, and that this guy is wrong. Now we can go ahead and erase those. Now let's number our chain. So we said that the best way to number our chain is this way. And now you know that it's going to have a 7-carbon chain, and that corresponds to the prefix hept. So we can go ahead and write hept for parent chain. Now let's talk about functional groups. Does this structure have any functional groups in it? It does not, right? So then we say that the suffix is going to be E. And what about unsaturation? Remember that unsaturation is asking if there's any double bonds or triple bonds. And we see here that there is a double bond. So what's the suffix for double bonds? Remember that the suffix is EN. Now for substitution. Remember we said that anything hanging off the parent chain is a substituent. So this guy here is a substituent because he's hanging off of the parent chain. The way that we name this substituent is by determining how many carbons it's composed of. And we see here that it's a CH3 group, which means that it has 1 carbon. Therefore, we can use the prefix meth. And because it's a substituent, we just put YL at the end, and then we call it a methyl group. What about stereoisomerism? Well, we just talked about it, and we actually named the stereoisomerism for this. But real quick, we just cut it in half like a sandwich, fill in our hydrogens, and we look to the left, and we see that on the left, this group is heavier, and that on the right, this group is heavier. And so we determine that this guy is totally cis. So now we gotta determine locations. So if we look at cis here, cis is just talking about our double bond. So we don't need to put a number for cis. If we look at our methyl here, we see that our methyl group is coming off of a specific carbon, and that's carbon number 3. So we gotta put 3 here. What about hept? Hept is not anything that needs a location, it's the amount of carbons that you got, so it doesn't have a number. What about ene? Well, that's telling us about our double bond, and so we know that our double bond has a specific location, so we gotta talk about that in our name. So we see here that it's occurring at carbons 4 and at carbons 3. So who do we choose? We choose the lower number. So we're going to say that our double bond is occurring at carbon number 3. As for our functional group, we don't have a functional group in this case, so we're not going to put a number here. So now, to use the FUPSS method, we go in a zigzag direction. So we say that this is cis, 3, methyl, nothing here, hept, 3, ene, nothing here, E. And so we just write it out in that direction. So we see here we got cis, 3, methyl, hep, 3, ene. So now we got to put in some dashes in our name. And so the key to this is knowing that dashes go in between letters and numbers. So for instance, here we have S and 3. So we got to put a dash here. And here we got 3 and M, so we got to put a dash here. Again, here we have T and 3, so we got to put a dash here. And between 3 and E, we got to put a dash here. A number cannot be next to a letter without a dash. What about here? Should I put a dash between methyl and hept? And the answer is no, because they're both letters. You might think that they're separate things, but this is actually one word. So you got to remember that the name of something is one word. So I'll just put that closer together. And so that's how you name the structure. Let's go over another example. So remember we said that we start off by numbering the parent chain. So you can ask yourself, which way is the best way to name it? Should I go from the right, 1, 2, 3, 4, 5, 6, 7? Or should I go from the left, 1, 2, 3, 4, 5, 6, 7? And the answer is, going from the right is better because it's going to put our alcohol group and our substituents on lower numbers as well as our double bond. So let's go ahead and name. So we got 1, 2, 3, 4, 5, 6, 7. Now, if you'd like, you can circle your substituents or highlight them to make them more obvious. So we got here an alcohol group, a methyl group, and another methyl group. So we see here that we actually have a functional group. And what functional group is that? That's an alcohol, right? And so what's the suffix for an alcohol? The suffix for an alcohol is going to be ol. What about unsaturation? We got any double bonds here? Yeah, we got one double bond. So we say that's going to be ene. What about parent chain? We know that it's 7 carbons long, and so we have hept. What about substitution? Well, here we got 2 methyl groups. So we actually say that this is called a dimethyl. Di meaning 2, and with regards to the methyl. What about stereoisomerism? So we actually figured out the stereoisomerism for this below, and we said that this guy was trans. If you don't recall this, you can go ahead and rewind. So now we got to determine the locations. So what's the location of this alcohol? And the location is occurring at carbon number 2. What about this double bond? Remember we say we take the lowest number, so between 3 and 4, we're going to take carbon number 3. What about parent chain? Does that get a number? No. What about substitution? Well, we got 2 methyl groups here, so what do we do in this case? Well, here we say that we got a methyl group at 3 and at 4. And to indicate that, we're going to write 3, 4. So now we can go ahead and put the name together. So remember we said it's suffix number, suffix number, suffix number, suffix number, suffix. And if there's no number there, you can ignore it. So we're going to go ahead and write trans dash 3, 4 dash dimethyl hept 3 ene 2 ol. That's a really long name, and sometimes that's going to happen for you. So now notice here how we have the dash in between numbers and letters, numbers and letters, numbers and letters, as we do here. But in between numbers and numbers, we put a comma. So that's a new rule for you. Whenever you got 2 numbers, you got to put a comma. And so that's how we name this structure. And so real quick here, I just wanted to show you that if we name this structure using the FUPSS method, we're going to find that we get the name transbute-2-ene. So let's go ahead and write that in. Transbute-2-ene. And the reason why I wanted to show you this is because sometimes you'll find that the name is written a bit differently. You'll see it written as trans-2-butene. We can automatically assume that this number here is going to apply to the double bond because there's no functional group and it can't apply to that parent chain here. So we can automatically assume that this 2 is going to belong to the location of the double bond. So I just wanted to let you know that you might see it written as butene or 2-butene. And these are exactly the same, and these are both acceptable. So here I have some examples laid out for you. Take a moment to pause the video and try them on your own. So now I just want to go over a few quick notes about each of these. So for example number 1, we see here that there is no substitution or stereoisomerism. Yes, there is a double bond, but that does belong to the carboxylic acid here. So we can't assign cis or trans to that. So when there's no unsaturation here, notice how we have the suffix "an" in the name. So you see here that we have butanoic acid. That's because this is an alkane and not an alkene. In number 2, we see here that there's a double bond, but it's non-stereoisometric, meaning we can't assign cis or trans to that either because of the 2 hydrogens it has on the right. And notice here how we give the carbon that belongs to the functional group number 1 because it takes priority over the double bond. So that's why we number from left to right. As for number 3, we have a cyclic ring, and when that happens, we put cyclo in front of the parent chain prefix. So we have cyclohex. And last but not least, number 4. Here we have 2 substituents, and it's important to note that the ethyl group goes first in the name, not the methyl group. That's because when we have more than one substituent, we use alphabetical order to list them. So here we have an ethyl and a methyl. Ethyl and a methyl. And so we ask ourselves, who comes first in the alphabet, E or M? And so because E comes first in the alphabet, it also will come first in the name. And listed below each example, I have all the possible names that you could have gotten as a correct answer. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!